Hello, my name is Lucky Kumar. I, along with me, have Krishna Mohan Roy. We are taking a deep learning course conducted by Dr. Arijit Mandal, Assistant Professor IIT Patna. In this video, we will briefly cover various methodologies to handle class imbalance problems in classification. Okay, let's get started with the agenda of this video. So, we will first define what is class imbalance, and then briefly we will talk about challenges faced by class imbalance, and then we will discuss about various methods available to handle class imbalance problems, and then we will conclude our video with a summary of various approaches to handle class imbalance. Uh, a data is said to be suffering from class imbalance when class distribution is highly unbalanced. That is one class is significantly low proportion compared to the other class. The class that has lower number of samples is referred as minority class, while the other is called majority class. So class imbalance is very prevalent in most of the practical use cases. Like credit card transaction fraud detection, anomaly detection, churn prediction. These are the few examples. And class imbalance can happen primarily due to two reasons. Either data collection is not done properly, or the inherent nature of the problem is of such type, like in the example of credit card transaction fraud use case. The former problem can be addressed through proper data collection strategy over time, and the later one, however, requires algorithm or engineering level handling techniques. So let's take the credit card transaction fraud use case. We have 10,000 total transactions, out of which 10 transactions are fraudulent transactions. Similarly, we can have another use case of classification of image into dog or cat with imbalanced class distribution, meaning number of images of dog is very less compared to the number of images of cat, or vice versa. So let's say for the fraud use case, we have built a model with 99.5% accuracy. But what does this 99.5% accurate model mean in this use case? Uh, think of another situation where we have built another model that flags each transaction as non-fraudulent transaction. We get accuracy of 99.9% in this case, although this is useless model and it does nothing. The situation of missing out on flagging an actual fraudulent transaction, the cost of missing out is very high. Now, we can think of something that can help us solve in handling the situation better. So we found that accuracy is not a good metric to basis our model performance. So can we then think of some other measures that works fine even in the case of class imbalance situation? So also while computing accuracy, the misclassification cost considered was the same for both fraudulent and non-fraudulent case. But from business perspective, identification of fraudulent case is of higher importance than of non-fraudulent ones. So what we set higher penalty for misclassification for fraudulent cases compared to the non-fraudulent cases. Uh, let's take hypothetical case where we set penalty of 100 for misclassification in fraudulent cases, and one for non-fraudulent ones. In this situation, accuracy of our useless model decreases to 90%. So can we somehow bring parity to the number of samples in both the classes? Or can algorithm level tweaking help handle this class imbalance situation better? Okay. So with this context, let's discuss about various methodologies researchers have proposed. Uh, The very basic approach to handle class imbalance can be randomly selecting only few samples from majority class and keeping all the minority class samples intact. Point to note here is, given we are selecting only a few samples from majority class, we might miss important data patterns. Also, the sample size for undersampled data is less, and hence it is easier to build model with reduced data size. The alternate arrangement to balance class can be taking repeated samples from mandatory class while keeping all the samples from majority class. In this case, sample size increases and hence training time might increase. So also, given we are taking some samples from mandatory class multiple times, it is adding redundancy and might lead to overfitting problem. So in both RUC and ROC approaches, we are sampling observations randomly, and hence data distribution of sample data might not match the data distribution of the original population. So one popular approach to handle it is using stratified sampling. We take strata variables to ensure distribution across a strata variable is maintained even after sampling. So, for example, in our case, fraud use case, let's take age and gender as strata variables. As we can see in the table, so the female of 25 to 35 years group actually has 18% population, both prior to sampling and post to the sampling. Proportion of samples in the strata group remains same after sampling as well. Now, knowing these strata variables might require domain expertise, and it might not be possible to cover all the underlying characteristics of the data using a strata variables. And hence, researchers have proposed cluster-based approaches. So now I will over to my friend Krishna Mohan Rai. He will discuss about some other approaches to handling this class imbalance problems. So Krishna.
Thanks, Lucky. So yeah, as Lucky was talking about the problems faced by stratified sampling method. So we might not be knowing a prior beforehand that know which variables are of higher importance. Even if you have domain expertise, then also using strata variables it might not be able to present all the underlying characteristics of data, and hence uh, people explored clustering based approach and they found some merit in following that approach. There has been several research work around sampling using clustering approach. However, we will discuss approach proposed by Lin. These approaches are easiest and very intuitive to follow. If there are m samples in minority class, so this approach suggests to form m number of clusters using majority class samples, and then you can either take center of each cluster as majority representative of majority class, combine with minority class, and follow up with building classifier models. However, when we are taking centers, we are not using actual observation, and hence there might be merit in trying out with actual samples that still preserves the underlying characteristic of cluster. So in other approach, the Lean suggests that can we take a point which is, let's say, closest to the center of cluster, and that way we can then combine it with minority class observations and follow up with classifier points. So as discussed, there are various other permutation combination as well that has been tried. Uh, now the other sampling method which is very popular these days among data scientists is synthetic minority oversampling technique, commonly also known as SMOTE. So in this approach, one observation from minority class is picked randomly, and then one observation from its k nearest neighbor is selected randomly. Uh, And then a synthetic point is generated in the line segment joining these two selected points. So let's say in this use case, we have tried to demonstrate a SMOTE in 2D space. And we have, let's say, selected X, this point X as a random point. And then all the points highlighted in gray are the points belonging to minority class. And these are basically the k nearest neighbor. Now let's say randomly you have picked point x1, right? So you can then create another synthetic sample z on the line segment connecting x and x1. So line segment is nothing but it is defined as, let's say, if z is a point on line segment joining x and x1, and it can be represented as w multiplied by x plus 1 minus w multiplied by x1, where w is nothing but a constant belonging to 0 to 1 range. Also, it depends on whether w is greater than 1 minus w or less than 1 minus w. The the vicinity of z will be decided. If, let's say, w is greater than 1 minus w, which, let's say, less, which is greater than let's say zero point 0.5, it means that z will be closer to x compared to x1. And hence, with controlling this w value, you can control the position of the synthesized point. Moving on, so uh, as we can see here in previous page, so let's say what if I select these 2 points, and now if I try to synthesize point between on the line segment connecting these 2 points, obviously the point might also fall around region here, which is, let's say, very closer to the majority class, majority class compared to minority class. And hence we can easily see that in case where there is overlapping class structure in data, we might end up creating that synthetic sample more closer to majority class compared to minority class. The other problem to note here is, let's say this Z is always going to fall between X and X1. So all the, no matter which two minority class observation you pick, the synthesized point is always going to lie between the boundary of those 2 points. And hence, in a way, we are introducing synthetic points inside the the overall boundaries of minority class, and hence the distribution generated after sampling is becoming more denser compared to what it was before sampling. So with these 2 problems, people have done various permutation combination, and they have tried various tweaking on top of a SMOTE. The researcher who first proposed this SMOTE algorithm has also explored combination of undersampling with the SMOTE technique. What it means is, so a SMOTE basically oversamples minority class. So researcher says that why not also do undersampling of majority class along with oversampling of minority class, and use the combination of these 2 to bring parity between majority and minority class observations. So other 2 in let's say in one of the extension of SMOTE, author has suggested 2 approaches that pick minority samples that lie closer to the borderline areas where majority and minority classes are kind of mixed up. In borderline SMOTE1 algorithm, author identifies this borderline samples using KNN approach, and then they apply a SMOTE on these selected samples. However, in borderline SMOTE2 approach, author basically allows interpolation of these points with majority class neighbor as well. So what I mean was that, let's say if you have selected one random point, in selecting the nearest neighbor, you can also allow a selection of majority class observation. However, while creating synthetic point, you create create a point that is more closer to a minority class compared to majority class. So as you can remember, by controlling the value of W, we can control the vicinity, whether it is going to uh, fall towards the closer to minority sample or majority sample. In other approach, author has followed contrary approach compared to what were followed in borderline SMOTE 1 and 2. So in this variant, which is called safe level SMOTE, it does not rely on boundary line points and overlapping samples. Rather, it synthesizes sample in the area of minority class. So given this approach is following risk averse approach, it avoids messing up with majority class because you're taking samples from the area where minority class is in purity, and given synthetic point is always going to fall on the line segment, and hence you are likely to end up in a region which is still pure. So there has been various you know changes that has been tried on top of SMOTE. One notable change that has been suggested using deep learning was DeepSMOTE, which basically extends SMOTE algorithm along by combining deep learning framework. So this framework basically consists of three major components. The first one is encoder decoder framework. Then it is followed by SMOTE based oversampling, and then they're also using dedicated loss function that enhances penalty factor for minority class. Moving on. Uh, in deep learning setup, basically minority class observations contribute less to the computation of gradient, and hence class imbalance can cause problem. Uh, Researchers have tried both random oversampling and undersampling approaches, and both of them have shown performance improvement. Uh, the other approach, named as two-phase learning, has also been proposed. In this approach, basically model is first trained, using thresholded data, and then parameter is tuned using all the whole entire data set. So basically, how thresholded data is generated is by undersampling, repeated undersampling until we reach the set threshold of n number of points. So Lee explores the various combinations like random oversampling, random undersampling, with combination of data augmentation, addition of noise, and also building model on the imbalance data set. The research showed that the undersampling approach performed better than augmentation techniques and noise addition technique. However, all the methods performed better than training classifier on imbalanced data alone. Sorry. So in one of the research, researchers also suggested dynamic sampling technique to perform classification on imbalanced image data with deep CNN model. So idea here is to oversample the low performing classes and undersample the high performance classes. So it is on the same analogy as human work. So basically, showing model less of what it has already learned. So where you're making less error, it means that you have learned the pattern. So I will present lesser data around those pattern, and then I will pass more data for the cases where model is throwing more error. So on this simple analogy, this algorithm is built. It has three components: data augmentation, transfer learning, and dynamic sampling. The dynamic sampling is a novel part, that self-adjust sampling rate, which basically allows us to extend our algorithm in dynamic scenario, and varying complexity of use cases can be addressed because of its self-learning nature. So for image classification use cases, data augmentation is also one of the very popular way to balance class, or even increase sample size where sample size is less. It helps getting larger data set, and hence help us in avoiding overfitting problem. Afzal in his work discussed about various data augmentation approaches like image rotation, cropping of image, even in cropping. Uh, uh, they've tried left, right, top, bottom, or even just cropping corner of the image, or cropping the entire image itself. They've also tried adding random noise to the image. However, this approaches has their own merit. One should also be very careful while using these approaches. So let's say if you are building a use case uh, uh, to recognize digit between 0 and 9. Now, if you use 180-degree rotation as data augmentation technique, you might end up converting 6 into 9 and 9 into 6, right? So depending on use case, you should pick the right methodology and right parameter of each methodology. So moving on to algorithm level approach. So researchers have tried various matrices like AUC, F measure, G mean in their research work, and you know these measures are less impacted compared to uh, uh, accuracy measures. The other approach, can be cost-sensitive approach that involves basically setting up higher misclassification cost to minority class. So, expression of cost might look like sum over all the observations. Cost of misclassifying one as 0, then where you have done that misclassification, plus the cost of misclassification 0 to 1, and then number of points where basically you have classified 0 as 1. The other approach which has been explored by researcher is changing decision threshold itself. So let's say if you are building a binary classification use case, in that case default probability is 0.5. What I mean by default probability 0.5 is, so model produces probability output, that is probability of occurrence of event. So if that probability is greater than zero point 0.5, you mark that as event will occur or event will happen. So or observation falls under class 1. If probability thrown by model is less than that, you'll say that no, observation falls in class 0. Uh, then people have tried varying that threshold. They've tried like changing it to, let's say, 0.6, 0.7, 0.8, 0.8, or even they have tried reducing in negative direction. And it all depends on the use case requirement, the requirement of trade-off between precision and recall. Multiple researchers have also tried modifying parameters of algorithm, like let's say SVM. In one of the research, ZSVM has been proposed that has shown good performance in selected setting. In various research, researchers have also explored optimization techniques to handle class imbalance problem. In one of the work, SMOTE has been tried along with particle swarm optimization and RVF. where particle swarm optimization is being used to find structure and determine parameter of RBF. The uh, other very popular method to handle class imbalance is one class classification. So this is a specific type of approach, where classification problem is addressed by analyzing only one type of instances. So model is built on using one class of observation, and then the other the other samples are basically scored using that model. Uh, OCC has been found very effective in use cases like anomaly detection, novelty detection, where uh, you know minority class is very rare uh, in occurrence. Uh, in density based, so there are two broad types of OCC method. One is density based, the other is boundary based. So in density based approach, basically one class classification method performs based on estimating the training data density, which is then compared to a threshold or model parameter to check if, let's say, uh, the actual observation is outlier or not. Uh, it works well uh, when sample is uh, uh, well defined density. Uh, some of the examples of one class classification are Gaussian method or GMA, or Gaussian mixer model or Poisson density model. Moving on, so there has been several extension of one class classification as well using other algorithms. One of such extension is one class support vector machine. This is kernel based approach, uh, which is designed on top of SVM. So this one class support vector machine basically is built uh, in such a way that it tries to develop a hyperplane that maximizes the distance between origin and separates outlier from inliers or normal observations, to say. The other variant called support vector data description. So this is also a kernel based or a boundary based model. This builds a hypersphere sphere with minimum radius, which comprises target samples. Any sample that falls outside of that hypersphere is considered as outlier. Typically, boundary-based model require less number of samples compared to density-based model. Because density-based approaches are mostly parametric models, so where uh, uh, sorry, a non-parametric model, and hence you require more sample to estimate those. Various other algorithms like k-means, PCA, deep learning has also been used in one class classifier setup by making certain tweaks to the core principle of these algorithms. The other way to handle class imbalance is using ensemble approach. So if we look at the high level steps involved in ensemble is basically there are three steps. One is where you do undersampling of majority class, you combine it with minority class observations, and then you build multiple classifiers, and then you take vote of all those classifiers that you have built. Several techniques which has combined sampling with cost sensitive learning has also been proposed, where people have tried to vary the penalty factor for different classes. Liu in his work proposed two algorithms called EG ensemble and balance cascade. So that learns multiple classifier by combining a subset of majority group with minority group. In a way, basically you're creating pseudo balanced training set for each individual classifiers. Then other variations which has been tried in ensemble setup are SMOTE boost, data boost IM, and JOS boost, which combines basically sampling method with ensemble concept. Sun in his work introduced three cost sensitive boosting methods, namely ADA C1, C2, and C3. So these methods basically iteratively increase the impact of minority class by introducing cost terms to basically update the ADA boost weight while training. Uh, Sun has also showed that this cost sensitive boosted ensembles work better than the plain ensemble methods where we use equal cost for all the classes. Okay, so let's summarize what we have covered so far. So random undersampling and oversampling method are very intuitive and easy to implement. They work well in general, and they are independent of underlying classifier algorithms, and that is the reason why they are so popular, and they found application in almost all the areas where classifier uh, classification model is built. Oversampling have shown tendency to overfit, while with undersampling we might miss out on important information because we are selecting only a part of information from the entire majority class sample there. Uh, SMOTE works well, and it is easier to implement, and there are several libraries available across all the different programming languages. However, as we discussed earlier, it can be problematic into scenarios where there are overlapping zone where minority and majority classes are overlapping. The other problem with the SMOTE is it creates more denser distribution of minority class compared to the original distribution because you are introducing these points on the line segment. Cost sensitive approaches basically uh, they as we discussed they different penalty factor for different classifications. They have worked well on various experimental setup. However, challenge with these algorithms are that prior to building algorithm you might not be able to know the cost or penalty factor for each class. And hence people might have tried they have actually tried combination of cost sensitive approach with varying threshold etc as well. Cluster based approach is basically enhancement over random sampling where you are making sure that the underlying characteristics of data is still represented even in an undersampled uh, population. However, given you have to build cluster first and then you have to follow up with building classifier model, etc. So this process is time consuming and requires more effort as an analyst. Ensemble method on the other hand have shown better performance compared to individual classifiers because of their underlying characteristics. They are able to uh, handle noise as well, and they are robust to noise. However, given you need to repeat this process multiple times, these are time consuming, and if these models are not built carefully, they might also lead to overfitting problems. Okay, so in conclusion, there is not not the sampling method or a unique method that is winner for all the use cases, and hence it makes sense for analysts or data scientists to try out various methods for their use case to find which one works best for their selected experiment. Undersampling methods basically help us build faster and faster model because the training time is typically less. Oversampling might lead to overfitting challenge in traditional models. However, researchers have shown that this overfitting problem is not as prevalent in deep learning scenarios as they are in traditional ML setup. Data synthesis can lead to condensed distribution, as we discussed in SMOTE approach. And for large data set, the good news is that both random undersampling and random oversampling both work well. Uh, so these are the reference materials that we have used to create this presentation. Uh, you can look at these reference materials to know more detail about these individual approaches. So obviously it was not possible for us to cover the entire research, because this is a hot topic and active area of research, and there has been several notable work uh, which are interesting in their core principle as well as in terms of their performance, and hence we urge you to explore various techniques. Before we sign off, we would also like to thank our instructor and mentor, Dr. Arjit Mandal, for providing us platform to cover the concept. We hope you learned something through this video. Thanks for watching the video. Keep learning. Until then, bye-bye.